Unit 5, the periodic table and the periodic trends. So we first start talking about the history of the periodic table. And in 1860, they had the first International Congress of Chemists, and they meet in Carlsberg, Germany. And they talked about measurements of atoms, their masses, and their chemical formulas. So, and then at this meeting, there was a presenter, Stanislaw Cannizzaro. He presented a method for measuring atomic masses and interpreting the results of measurements during the First International Congress. And then, as a result of this information and other information that other scientists had actually presented or discovered, Dmitry Mendeleev, he made the first periodic table. So he used the new information regarding the atomic masses in his chemistry book he was writing. He wanted to write a book because he was teaching chemistry and there wasn't a book that was available. So he decided to actually write his own book. So he organized the elements according to increasing atomic masses, which is different than the periodic table today, because we do it increasing atomic numbers. He did it based on increasing atomic masses. As a result of this organization, he noticed that elements with similar properties appeared at regular intervals called periods. In 1869, Mendeleev published his first periodic table of the elements, in which the elements of similar properties were grouped together. And this part is kind of amazing. He left several empty spaces in his periodic table, later predicting the properties of these unknown chemical elements. Later, these elements were actually discovered and found to have the properties very similar to what he had actually predicted. Okay, so let's take a look at what that looked like, his first periodic table. So let's talk about a periodic table. So Moseley and the discovery of the periodic law. So Henry Gwen Jeffreys Moseley, so he lived from 1887 to 1915. He was working with Rutherford, who we heard before. He discovered the positive charges of the nucleus increased by 1 unit from one element to the next. So elements are arranged as they are in a periodic table. His work led to the recognition that the elements of a periodic table should be arranged by atomic number, not atomic mass, and act as the basis for the organization of the periodic table. And another discovery that was made is a periodic law, and this was possible because of the arrangement according to atomic number and not atomic mass. This periodic law states that the chemical and physical properties of the elements are periodic functions of their atomic numbers. Periodic means that there is a repeating pattern. In this case, the physical and chemical properties are repeated at regular intervals. As a result, elements of similar properties occur in the same column. And the modern periodic table, since Mendeleev made his first periodic table, 40 elements have been added. Right? In the modern periodic table, the elements are arranged in order of increasing atomic number and non-atomic mass, as was done in Mendeleev's periodic table. As a result, the properties of elements occupying the same column have similar physical and chemical properties. Now, if you look at the 40 elements, I mentioned this before, but you're not going to find noble gases because they're inert, right? So in Mendeleev's periodic table, he didn't have the noble gases because they're inert, non-reactive, so it's very difficult to discover when they're present. An interesting thing that if it's an example of, we mentioned that he predicted elements, and he actually predicted what those elements, what their properties would be. An example is gallium, and gallium is an unusual metal. If you put gallium in your hand, the heat from your hand will cause the metal to melt. At room temperature, it's actually a solid. So that was discovered after Mendeleev wrote his periodic table. And when they discovered it, they were really surprised that what he had predicted as far as its physical and chemical properties was very close to what it actually had. So, okay. Now, we'd mentioned before, so groups. The vertical columns in the periodic table are called groups. And I realized I made a mistake over here. I should have said here the elements of each. Yeah, I put period over here. This should actually say group. I hope that didn't. Sorry if that caused any confusion. But this right here, I wrote period, but it should say group. Have similar physical and chemical properties. So if I do this, if you look at the periodic table, the columns going down the groups, each one of these, let's say this is group 18, the noble gases, they will have similar chemical and physical properties as you go down from each element in that group. The periods, these are the horizontal rows of the periodic table. And there's a repeating pattern of chemical and physical properties when moving from left to right down the periodic table. If we have two periods, okay, and I'll draw some groups going across. So this is just two periods. If I go from this element to this element, and I look at their physical and chemical properties, they're very similar. And if I go across to the next group down the column, as I go from go down the group, they're still going to have the same physical and chemical properties. So as I go across the period, I'm going to pass groups 1 through 18. And then when I go down to the next period, I'm going to cross groups 1 through 18 again. And I'm going to see that as I go across group 1, the physical and chemical properties are going to be similar. Group 2, group 3, and so on and so forth. So that's a periodic law. Okay? So, and I mentioned this before, elements added since Mendeleev. Mendeleev's periodic table included the noble gases. All right, and I mentioned before that they're non-reactive, and that's why it was difficult to. So ultimately, the properties, both physical and chemical properties, are really determined by the electron configuration of the atom. Now, if you look at the electron configuration, groups 1 through 2 and 13 through 18, the outer electron configuration is the same for each element occupying the same group. Also, the number of valence electrons, which are the outermost electrons, is the same as the number of the groups for 1 and 2, and the same as subtracting 10 from groups 13 through 18. So groups 13 has 3 valence electrons, group 14 has 4 valence electrons, etc. Group 3 through 12, the elements of this highest and the highest occupied energy levels is not identical in all cases, but are similar. And that's why they have similar properties. So electrons in the highest energy level will determine the reactivity of an element. The length of the period is determined by the sublevels being filled. Okay, so the longer the period, the larger the sublevels are they're actually filling. So we can divide the periodic table into blocks of elements, and those blocks are whether the elements are being filled in the S, P, D, and F sublevels. All right, so the S elements, these include groups 1 and 2, the highest energy level being filled is the s orbitals and include. So these include the alkali metals. All right, and this is group 1, except for lithium. They're silvery in color and have melting points lower than the boiling point of water. The alkaline earth metals include group 2 and are less reactive than group 1. They're harder, denser, stronger, and have a higher melting point than group 1. Hydrogen and helium are included in the S block, but are non-metals. And so now we have the D block elements. This includes groups 3 through 12. There's some of the deviations in the filling of the D sublevels, and they're called the transitional elements. So D block elements are referred to as transition elements, and the D block elements are all metals. They have the following characteristics: good conductors of electricity, high luster, they shine, high melting point, except for mercury. All right, so mercury is actually a liquid at room temperature. Less reactive than the S block elements. The sum of the outer S and D electrons is equal to the group number. And they have the P block elements, and that's groups 13 through 18. The P block elements, together with the S block elements, are referred to as the main group elements. The number of valence electrons is equal to the number of the group minus 10. So the properties of the P block elements vary greatly. Group 17, they're called the halogens, are the most reacted non-metal, interact with metals to form salts. Group 18, the noble gases, are the least reactive elements. So the F block elements include the lanthanides and actinides. The lanthanide elements are elements following lanthanum and before hafnium in period 6. And for convenience, they're often located separately along with the actinide elements below in the rest of the periodic table. The actinide elements follow actinium and are before the element rutherfordium. All right, now let's look at the electron configuration and periodic trends. So what we're talking about here are some physical characteristics and the trends that we start seeing with them, or some chemical trends that we start seeing in the periodic table. The first one is the atomic radii. The electron cloud determines the size of an atom. And the nucleus taking up only a tiny amount of space. The size of the atom is not definite. The atomic radius is 1/2 the distance between the nuclei of identical atoms joined in a molecule, diatomic molecule. If you look at the periodic trends, there's a gradual decrease in atomic radii across periods from left to right, and this results in an increase in the positive charge of the nucleus as additional protons are added. Group trends, if you look at gradual increase in atomic radii when moving down the group. And that makes sense because as you go down the group, the atom gets larger. So now let's look at ionization energy. Right? Ionization energy, or the first ionization energy, is the energy required to remove one electron from an atom of an element, forming a positive ion called a cation. Right? If you recall, an ion is an atom or group of atoms that has a positive or negative charge. If it has a positive charge, it's called a cation, which results from the loss of one or more electrons from a neutral atom, or a negative change called negative atom called an anion, and it results from the addition of one or All right, more electrons form a neutral atom. Ionization. This is the process that results in the formation of an ion. Periodic trends. Groups of group 1 elements have the lowest first ionization energy and tend to lose electrons most easily, resulting in their reactivity. However, group 18, on the other hand, has the highest first ionization energy, which results in a very low reactivity. If you look at the group trends of the main group elements, ionization energies generally decrease down each group as the size of the atom increases. This occurs since more electrons are located further from the nucleus. As a result, inner electrons shield the positive charge of the nucleus from the outer electrons, and there is less positive charge acting as an attractive force holding the outer electrons of the atom. Formation of a positive ion. Electrons can be removed from positive ions as well as neutral ions if sufficient energies are used. So the first ionization energy is the energy required to remove the first electron. All right, so let's put that. Okay, so your first ionization energy. And the second ionization energy is the energy required to remove the second electron. And it's going to take more energy to do that. Then the third ionization energy is the energy required to remove the third electron. Each successive removed electron require additional energy. So let's look at some of these terms that we've talked about so far. So previously we talked about the atomic radii. This is showing you the atomic radii, and so you have two atoms, and they're both the same element, and they're bonded together. All right, so this atom right here, all right, so this right here, these are two atoms, the same element bonded together. We call that a diatomic molecule because they're both the same element. What you do is you measure the distance between the nuclei of those two atoms and you divide it by 2. So here it's 128 picometers, and you divide that by 2. That's what they're showing down here. So the radius is half that number. So the radius is 65 picometers. So we'd say the atomic radii is 64 picometers. Right? And then if we look at down here, this is showing you the atomic radii on the periodic table. So the size of these green circles is going to tell you the size of the atomic radii. And you can see as you go from left to right, right? So if you look at, let's say, potassium over here, and you go, so this is period 4, you go across from left to right, you can see the trend. It's a little subtle, but you can see the trend generally is that the atomic radii become smaller. All right, and again here you can see general trend is it's going to go, if you go from left to right, it's going to become smaller. And if you go down, let's go to group 13. If you go down the group, generally you'll see that the atomic radii becomes larger. In group 1, it's much more evident. Right? As you go down, the atomic radii is becoming larger. And it makes sense because as you go down any group, the atom is going to be larger. It's going to have more protons in the nucleus and more neutrons nucleus, and it's going to have more electrons. All right. And so also there's a variation in the ionic radii as well. And this may help understand a little bit more. Aluminum, right over here. Aluminum, if you look at it, it has an ionic radii the atomic radii is 118 picometers. If I remove 3 electrons, it then is only 68 picometers. Right? That's why it has a positive 3 charge, because it's lost 3 electrons. And so the remaining electrons are closer to the nucleus, which is the positive charge. It's going to pull on those outer electrons that are left with a greater force, and the atom's going to be smaller. So sulfur over here, you can see the neutral atom is 104 picometers. If I remove, if I add two electrons, it's going to actually increase in size. Right? So why is that? Those, if I add electrons, they're going to be on the outermost electrons. They're still further away from the nucleus. The influence of the positive charge of the nucleus is not going to be as strong on those 2 electrons you just added. So it's going to, they're going to be actually be a little further away, a little further away, which is to increase the size of the atom. So what can you gather from here? If I make an atom a positive charge, right, remove electrons, the ion's going to be smaller than the neutral atom. If I add electrons to a neutral atom, the ionic radii is larger than the atomic radii. All right? And we talked about the first ionization energy. Okay? This is showing you, these numbers here are showing you the ionization energy, and it's in a unit called the kilojoules per mole. All right, so if you look at, let's say sodium, because this is something, so sodium is an atom, an element that we're familiar with. Its first ionization energy is 490 kilojoules a mole. If we go across, you can see across here, you can see how it is actually a lot greater, especially if you look at the noble gases in group 18. Their first ionization energy is a lot greater. So it holds on to those valence electrons with a lot more force. So it takes more energy to break those away. And this helps actually determine the behavior of atoms in a chemical reaction. Generally speaking, right, groups 1 and 2, when they take part in a chemical reaction, they're going to lose their valence electrons, in part because it has very low ionization energy. Where if I look at, let's say, the noble gases, not the noble gases, the halogens, they're going to gain electrons. Right? They're not going to lose electrons because they're pretty high first ionization energy. And then if you look at noble gases, their first ionization energy is really high. So they're not even going to be taking part in chemical reactions because they're holding on to their electrons, and they have as many as they would like. All right, so I move this around. So electron affinity. Electron affinity is the energy change that occurs when a neutral atom acquires an electron in the gaseous state, forming a negative ion called an anion. The first electron affinity, the energy change that occurs with the addition of 1 electron to a neutral atom. Right? The second electron affinity, this is the energy change that occurs with the addition of a second electron to an atom. And we have chemical reactions occurring, or chemical changes occurring. And it could be a chemical reaction. It also could be a physical change that occurs, like going from a liquid to a solid, or a solid to a liquid, for instance. If those changes occur and they release energy in the form of heat, that energy is that change in energy is referred to as being exothermic. Right? So exothermic Energy is released from the atom when an electron is added. So in chemical reactions, you can have a reaction being exothermic or endothermic, but also physical changes can be exothermic or endothermic. So exothermic, you're losing energy in the form of heat. Endothermic, you actually have to add heat to it. So energy is added to an atom when an electron is added. And this is forcing the atom to accept the electron. All right, so how would I know the difference? If a chemical reaction is cold, it's endothermic because it's absorbing heat. If the chemical reaction is hot, then it's an exothermic. It's releasing heat. So if I burn paper, that's an exothermic reaction because it actually is releasing energy. Periodic trends. Halogens, group 17, gain electrons most easily, and is a reason for their high reactivity. Electron affinities become more negative across each period within the p block. Atoms of groups 2 and 18 are least likely to gain electrons, which results in their positive electron affinity. Group trends, there's no regular trend of ionization energy of groups of elements. Formation of negative ions occurs with the addition of an electron to a neutral atom and the addition of additional electrons to a negative atom. It's always much more difficult to add additional electrons to a negative ion. The second electron affinities are always positive. In order for an atom to achieve the noble gas electron configuration, ions with negative charges greater than 1 can be formed. Ionic radii. Ionic radii is half the diameter of the ion in an ionic compound. And a cation, or cation, is a positive ion. An anion is a negative ion. Periodic trends, within each period, metals at the left form cations, and nonmetals on the right form anions. And beginning with group 15, anions are more common than cations. Group trends, down a group there's a gradual decrease in ionic radii. And then I have here valence electrons. We'll talk about that the next. But valence electrons are very important in understanding chemical reactions. So we're going to define valence electrons. So valence electrons are the outermost electrons of an atom. It is the valence electrons that are lost, gained, or transferred between atoms. That's a chemical reaction. So when you have if an atom loses an electron, gains an electron, and they're transferred between atoms, that is a chemical reaction that's occurring. And it is those valence electrons that actually determine the reactivity of an atom. And another characteristic that's important is the electronegativity. And this actually determines the type of chemical reaction that an atom will take part in. The electronegativity is the measure of the ability of an atom in a chemical reaction to attract electrons. The element fluorine has the greatest electronegativity with an electronegativity of 4. All other elements have electronegativity relative to that of the element fluorine. Periodic trends, across each period there is a gradual increase in electronegativity. Nonmetals are generally more electronegative than metals. Group trends, within groups, the electronegativity either decreases down the group or are very similar. Larger atoms attract electrons less and have a lower electronegativity. And this is from Wikipedia, but this is a table. It's actually shown the periodic table and the electronegativities. So if you look at this, for example, find fluorine. We find fluorine over here. That has the highest electronegativity. Oftentimes referred to as 4, or rounded to 4. All of the other atoms in the periodic table, all the other elements in the periodic table, they're all compared to the electronegativity of fluorine. It has the highest. And if you go over here, let's go down to the metals in groups 1 and 2. You notice over here that these have the lowest electronegativity. So if these metals here in groups 1 and 2, if they bond with, let's say, the halogens in group 17, they will form, or as I say, when a reaction occurs between them, the metals will lose an electron, and that halogen will gain the electron. And that's because it has such a great difference between the electronegativities of those atoms. So you can think of it this way, is that when the electronegativity is greater, the pull that it has, or how much it's going to actually grab other electrons, is greater. And the lower that electronegativity, the less force that an atom is going to have as far as holding on to its valence electrons. And again, it's going to be the valence electrons that are going to take part in that. And then you can see that there's a transition. The transition elements, they have very similar electronegativities. All right. All right, this is the back to the that open textbook. And you can see on here, this is actually showing you how the atomic radius is determined. So you can see that it's, so let's look at this one right here. All right, so you can see over here that the radius is 64 picometers. So you take the distance between the two nuclei, you divide it by 2, right? So in other words, it's the distance halfway between them. And that's going to be the size of your element. And if you look on here, you can see down here, this is a table showing you the atomic radius of the elements. You'll notice over here, lithium and beryllium. All right, let me move this here and I'll draw it. So let's say, let's go to sodium. Sodium, magnesium. You go across, and you'll see that, right, the size, there isn't a huge difference in the size. But then when you start going down to period 4, you will see the trend is, if I go from left to right, that the atomic radius is getting smaller. It happens for a couple of different reasons. If you think about it, if I go from let's say potassium over here, I go across, what's happening to the atomic number? It's going up. In other words, there's more protons. The more protons you have in the nucleus, the greater or stronger the positive charge is, which is going to pull on those electrons. Right? And this is particularly true. You can see if I go down to period 5. If I go from left to right, right, you're seeing that atomic radii is becoming smaller and smaller. And then if we go down a period, right, let's look at 15. You go down the period, the atomic radius is becoming larger just because the atom's getting larger. Right? And you can see this really in group 1, kind of epitomizes that. You can see if poor little hydrogen is up here, how small it is. Lithium's a little bigger. Sodium's bigger. Potassium is much bigger. Rubidium, cesium, franconium, they're all larger as they go down. And so the atomic radius is larger because the atom is larger. And then if I go from left to right, the trend is that the atomic radius has become less. So this is a table that shows the first ionization energy of the element. So what do you mean by first ionization energy? That means it's the energy that's required to remove the first electron. It takes additional energy to remove a second or third, so you'd have to have a different table that would show the energy required for that. So if you look at let's say sodium, right? Sodium, as we mentioned, you saw the video of how reactive that is. Sodium has a very low first ionization energy, and that's why it's reactive. So in group 3, now let's go all the way over to argon in period 3. All right, so in period 3, if you look, it's 1,520 kilojoules per mole. That's much more energy that's required to remove the first electron, and that's why it is very stable. You notice that the higher the first ionization energy is, the more stable the element is. Or what I should say, it's least likely to lose an electron, right? Which is part of what will make it reactive. Okay. And if you look at magnesium, 730. So as we go across, as it become greater and greater. And I shouldn't say that its reactivity is just determined by its ionization energy, but whether the type of chemical reaction it's going to take part in will determine it. So if you look at groups 1 and 2, these have a relatively low ionization energy. So if they take part in a chemical reaction, they're going to lose an electron in that reaction more than likely. Or if we go over here, I'm going to skip across the transitional elements and go across here to the more of the main group elements. So if I go, let's say from aluminum towards chlorine, you can see that the first ionization energy becomes greater and greater. The trend is that, except for the noble gases, if these chemicals take part if these elements take part in a chemical reaction, the tendency is the stronger the first ionization energy is, it's least likely to give up an electron and probably going to get an electron or receive an electron or possibly share an electron in a chemical reaction. All right, this is the open chemistry textbook. I'll leave links for this. This is showing Dmitry Mendeleev. So this picture over here is Dmitry Mendeleev. Right here. And this is the periodic table that he made. And it's obvious from looking at that it looks different than the periodic table of today. But what you'll notice is up here at the top, he has the groups labeled. And then so these are the groups going down. All right. And then these are the periods going across. Now, what he found was that in groups, they had the they're very similar properties. What you will also know is that we're missing the noble gases, and you're not going to find them on here. They weren't discovered till later, and that's because they're inert. They're very difficult to try and find because they're not reactive. Okay, so that's the periodic table that Mendeleev made. And we can see over here, this is showing the lanthanides down here. All right, so your lanthanides and your actinides. So these are the two periods that you see below the main part of the periodic table. And over here, group 18, these are the noble gases. You can see some of these other groups are also names. Some of the ones that you will see that's common is group 17. These are called the halogens. Group 1, the alkaline metals, and group 2, the alkaline earth metals. And then this over here, groups 3 through 12. These are called the transitional metals. All right, now why can we call these groups a specific name? Well, alkali earth metals, they're all in group 1. They have similar chemical properties, with the exception of hydrogen. And then group 2, the alkaline earth metals, these have similar properties, so that's why we can give a name to it. Noble gases, right? They're non-reactive. All of those gases in there, they have similar properties because they're in the same column, same group. Halogens also the same thing. And then your transitional metals, these do as well. Okay. So this is a diagram of the periodic table. What I did was I labeled the parts according to whether it was S, P, D, and F. So you can see over here groups 1 and 2. Right. That's the S block. All right, so this right here, this is the S block, groups 1 and 2. And then 3 through 12, right? This is the D block. And then groups 13 through 18, with the exception of hydrogen, that's the P block. And then down here, the lanthanides and actinides, these are the F block. All right. Now, something that I will point out here that's important to understand is you'll see over here in the periodic table 56 and then 88. Then it goes to 71. Well, and it goes from 86 to 103. What does that mean? Or why does that happen? That's because the lanthanides and actinides, the F block, actually fits in this space between here. So you'd actually have to stretch the periodic table out to actually fit that in there. So why they put the F block down here? It's for convenience. So the periodic table will fit better when you're in illustrations like this. That's the only reason why. And so if you're really trying to understand the periodic table, you want to think about this being here. So to show you the reactivity of sodium, for instance, I'll show you this little video. So this is sodium, and they're adding water to it. And you can notice now, see, so sodium will react with water. And think about it, that sodium is in salt, sodium chloride, but this is just pure elemental sodium. Okay, actually, let's look at that again. So if you look, you see the water striking the sodium, Na, and what's happening is it's reacting with it in forming sodium hydroxide, so it's mixing with water. So it's a very strong reaction. So that illustrates how reactive the groups 1 and 2 elements are.